So now that we've dealt with some preliminaries, we're ready to give the formal definition of a spectral sequence. Now there are a couple different types, so let's say a cohomological spectral sequence, which I'll usually just abbreviate SS. This is going to be a sequence of bigraded R modules. Okay, so those are just graded R modules, but the bigraded is that I'm telling you we're grading over Z cross C. So these are bigraded R modules, and each one of these is our rth page of the spectral sequence. So I've got ERPQ for R greater than or equal to 1, so that's telling me the sequence. I've got a sequence of pages, and P and Q should be integers, or I might write sort of the bi-degree lives in Z cross C. Okay, and so I've got this sequence of these bigraded R modules, one corresponding to each page, together with some differentials. And remember we said that these differentials go from the rth page back to itself, but now let's get really precise. So it should go from the PQth spot to, this is going to change the degree, so to the P plus R, comma Q minus R plus 1 spot. So really there's one of these for each PQ, but I call them all DR, kind of by abuse. And these should be differentials in the sense that they square to 0, so that we can take cohomology with respect to these, or homology. And another way to say this is that these differentials have bi-degree, I'd call it R comma minus R plus 1. And I might refer to the total degree, which is just the sum of those, and that's always going to be 1. So notice this depends on R, so these differentials are going to go over and, I guess, over and down more or less depending on which page we're on. And then we know we're supposed to take cohomology to get to the next page, so ER plus 1 is just going to be the cohomology with respect to this differential. Now let's make that a little bit more precise. So when I look at the R plus 1 page and I look in the PQ spot, how do I get it? Well, I should take the kernel of the differential going out of that spot. So that's ERPQ. Oops. Sorry, my eraser got a little wild there. Let's try that again. Okay, ERPQ. Trying to make this legible. And we already know that on the rth page, that differential goes to ERP plus R, Q minus R plus 1. But then we should mod out by the image of the differential coming into the same spot. So that differential should start at P minus R, Q plus R minus 1, and land at the PQ spot. So all I'm saying is we take the kernel of the differential going out of that spot, mod the image of the differential that comes in, of course. And remember that we talked about the E infinity page, and this isn't actually necessarily a page in our spectral sequence. This just means the colimit over R of these pages. Okay, so that's the definition of a cohomological spectral sequence. And then this E infinity page hopefully has some useful information that's going to depend on some convergence. So let's define that. Oops. Okay, so we say the spectral sequence converges, And what does it converge to? It's going to converge to a graded module. So the graded R module, let's call it M. And now here I'm grading on the integers. And we often write, and I think you've all seen this before, something that looks like ERPQ, maybe for some particular R that we know well, arrow to MP plus Q. Okay, so this is our notation for saying our spectral sequence converges to this graded R module M. When does that happen? Well, we say that if you look at each spot, so for each bi-degree PQ, we want some kind of stabilization there. So we'll say there exists an R naught so that drPQ, I just mean the differential out of the PQ spot, is 0 for R greater than or equal to R naught. So that's just saying, in some sense, that the maps out of this stabilize. Remember, to get to the next page, we're always going to take the kernel of this differential. And so if this differential is 0 forevermore, then that kernel has stayed the same. So, okay, that's not a statement about the image, but that does tell us that, I guess, let me even write that. So this is going to tell us that ERPQ surjects onto ER plus 1 PQ. And so on for all R greater than R naught. Now, we also need to involve this graded R module M. So I'll say there's a filtration of this graded module so that, well, what do we want? For each n, we look at the E infinity page. We look at the P n minus P spot. So, of course, that's just the colimit over R of the P n minus P spots. And what we want is that this is isomorphic to the associated graded component we take the associated graded for whatever filtration this is, so just saying there is some filtration, and then we look at that nth associated graded component. Okay, so this, at this stage, I think is a little opaque, and it'll make much more sense when we actually have some concrete examples and can talk about this filtration and the associated graded and how they relate. But essentially, that's how we mean that this isn't really, it isn't really that at the end we cook up this module M star, because we're not going to get that module, but there's some filtration of it so that we're getting the associated graded for it. Okay, let me also say that, I'll leave that one there for a moment. So I started with a co-homological spectral sequence, and I like to think about cohomology because we have this nice ring structure there. So I'll tend to use that, but we could also have done all of this for the homological setting. Part of what's confusing about that is that the degrees look different. So let me say everything here is almost the same for a homological spectral sequence. Well, what would that look like? We'd have some ERPQ. We usually put the by degrees downstairs for the homological situation, and we just say that this converges to some MP plus Q, and now we need our differential to have a different degree. So this is going to go from the PQth spot on the R page to now it's the P minus R, Q plus R minus 1 spot. Okay, so this really has by degree. Well, now it's going, let's see, it's going to the left R, so minus R, and then up R minus 1. Okay, and the total degree here is minus 1, as we'd expect for something homological. Okay, so that's a lot of sort of technical stuff, and part of what we want to do in this course is see a bunch of examples so that we get more comfortable with all of this machinery. But the upshot, maybe for the moment, is when we talked about the Serre spectral sequence, remember that was associated to some fibration, or you could think fiber bundle. And here F is the fiber. Then when we write E2PQ, what we do is we say, actually we know how to specify that. So it's the pth cohomology of the base with coefficients in the qth cohomology of the fiber. And we wrote this arrow to HP plus Q of the total space, E. Well, really this is just shorthand for saying there's a spectral sequence. Where we know what the E2 page is. And we tell someone, yep, you can go and put in all those PQ bidegrees by just computing these cohomologies. And it's converging to, well, I sort of loosely say converging to the cohomology of the total space, but actually it's converging to an associated graded for some filtration of the cohomology of the total space. Maybe I really mean of that whole ring. So, of course, when we talk about the Serre spectral sequence, we'll need to understand what filtration that is, how this is showing up, and then part of the problem in computing a spectral sequence is even if you can compute it and you get to the end, well, now you just have an associated graded, and you have to solve all of these extension problems to actually learn about the result. Okay, so we'll see all of this in much more detail. What I want to do in the next video is talk about a particularly nice case where we have a first quadrant spectral sequence.